So yeah, so looks like the big boss is not here, so I'm in charge, I guess. Okay, so today we're very happy to hear about variations of one of Fefferman's very old theorems. So I'm excited to hear about that.
Thank you very much. So it's I will try to give an overview of things that I'm interested in. So the new part will be some new results that I have with Javier Parcet and Eduardo Tablate here in the room. So I do not come from harmonic analysis, but it's about harmonic analysis, and it's about harmonic analysis questions that occurred in my investigations of things that are more related to semi-simple Lie groups, semi-simple arithmetic groups, and operator algebras associated to them. But I will try to explain why natural questions in harmonic analysis. So very basically, the topic of this question is a very. I want to discuss a general phenomenon that is one of the reasons why we are doing analysis. Many questions in analysis are difficult and interesting because if we want to understand the fine integrability properties of a function f and looking just at the value of its Fourier transform, that's complicated. Okay, so this is one question that is hopeless in general, but making any kind of progress in this is great. And what I want to advertise is actually there is a question of the same flavor with different object that is behaving very similarly, to my surprise, more similarly than I first expected. And so the other is the fine spectral properties of a matrix A by just looking at the entries. Okay, so, and well, of course, when I say that this is in general it's complicated, of course, there is one thing that is completely obvious that we can do, is that we have the Plancherel formula. So we have the integral of f squared equal to integral of the Fourier transform. So on the L2 level, this question is obvious, but my point is that actually this is the only kind of thing that we can say that easily. And in the same way, so if A, let's say if A is self-adjoint, then in the same way we have the sum of the squares of the eigenvalues is sum of the squares of the entries. So that's kind of obvious, but apart from that, we cannot tell it very much, and that's the theme of today. So any kind of small progress that we can do on this kind of question is interesting. So let me start with something that is very, very old. I will start by discussing some questions about convergence of Fourier series. So I will start by an old theorem of Marcel Riesz from the 1920s, that says that if you take a function, a periodic function in one variable, then we have that f is the limit in LP of the sum of its partial Fourier series. Okay, and for that, it's important that we make some restriction on f, and it's true when when p is not in, it's not L1 and not L infinity. Okay, this is a theorem. If it's not a very difficult one, but it's a theorem, and it's essentially by some very easy stuff. This is equivalent to saying that the Hilbert transform is a bounded operator on LP for every p that is not, well, every p in this range. Okay, the very natural question, if you're not familiar with that, so what about in higher dimensions? So what about in LP of the a periodic function in RD. So this, if it's if you've never seen that, you would expect the same is true, but actually we know that it's not. And what is rather easy is that if P is not too close to 2, then there exists a function f such that it's not equal to the sum of its Fourier partial Fourier series. Okay, and what is it? I was a bit fast here, but when I write, well, did I mention the Fourier coefficients are indexed by the z to the d, and when I put the norm, I meant the natural norm of the two norm of the coefficients. And actually, there is f, and the function is radial. There is a radial. Well, I think if you do this in RD, not periodic one, when you just take the integrals, then you can find a radial function in RD such that that is not the limit of its truncated Fourier series and the Fourier transform. And actually, in the 50s, it was conjectured that for P that is between 2 and this critical parameter, actually this should be we should have the conversion convergence should hold, and this was a conjecture, and this was disproved to I believe to a great surprise by Charlie Fefferman, and that's his Ball multiplier theorem. And this is easy, and what is not easy at all. It came as a surprise. It's the same is true for every P. That is not, of course, by the Planchel formula, the L2 case is not interesting. It's obviously true, but we are interested in finer. Okay, maybe this is, well, in a sense, what we learn from that is that this is actually it's a very specific question to decide to truncate the Fourier series just brutally, but we all know this is much easier than anything that is on the board here. Is that if you truncate in a smooth way, then we can do much better, and this was proved by Riesz' PhD advisor by Mikael, that if we define in dimension 1, if we define this César average of this truncation here, so the kernel will be 1 minus absolute value of n divided by n, the positive part, then we have that f is the limit of this. Okay, this is true, and this is even true for P in the endpoints if for P goes infinity if f is continuous. Okay, that's much easier than anything, and and therefore the natural question is, okay, so this is interesting because it says that we can reconstruct the function in LP in an efficient way in terms of its Fourier coefficient. Okay, and the question that I want to address today is what about other groups than Z or Z? Okay, so here in what I discussed so far, the Fourier series were indexed by the group Z or ZD, but I want to take different groups, and it is essentially
non-abelian, actually.
Yes, I will take the non-abelian, exactly. Because actually, if the group is abelian, you can do exactly the same. Well, it's a small exercise to see that you can mimic the Fourier kernel and construct and have ways of reconstructing the function in LP in norm for any abelian group. And so, what about this? And this, of course, even non-abelian. So maybe I have to say shortly what I mean by that. So since the group is not abelian, I don't have a nice Fourier transform. So we need to just adapt the definition, and we are working with operators and not functions. So if gamma is a group, I will write when gamma is a group with no topology, and then sometimes I will take for gamma some locally compact group. But it's the same kind of difference between Fourier series and Fourier transform. So it's a bit more technical, but it's nothing important. So if gamma is a group, and if I have, I will define LP of gamma hat. So just a notation. This is the set of convolution operators on L2 of gamma, such that so it's the convolution by the convolution operator, let's call it T, such that if I consider the absolute value of T to the power P, and I take this matrix coefficient, I get something finite. So maybe what I best way to say it is I take all convolution operators, I equate them with this quantity, which is a norm, and I take the completion of that, and this gives me the LP space of the group. And why is this a sensible definition? Okay, if gamma is an abelian group, convolution, Fourier transform, exchange, convolution, and multiplication. So the convolution operators on L2 of gamma are exactly the bounded continuous functions on the Fourier on gamma hat, and raising the operator in the functional calculus to the power p is just taking the function and raising it to the power p, and taking this scalar product, exactly taking the Fourier coefficient of 0, which is just taking the integral of the function. So this is when you have an abelian group, I'm just writing in a complicated way the usual definition of the LP norm, and this is an object that makes sense. It's again a norm. And so the question that I raised here, so is it true that for every group, even non-abelian, there is a sequence, there is a way to reconstruct any element in this space by truncating in a possibly smooth way its Fourier coefficients. And and in this case, so we know that the answer is yes, if gamma is abelian. This is essentially Fefferman's theorem, plus some structure of abelian group, so it's very easy. It's also true if your group is amenable, so this is not central, so if you don't know what amenable is, we will go very fast on that. So this is kind of the obvious case, and the first non-obvious case is the second surprise that happened in this subject is the theorem by Fagero to prove that actually this is also true for free groups. So the free groups are groups that are very far from being amenable. There were very strong reasons to believe that amenability was needed here, and this was really an important result that.
How do you order?
Sorry?
So, I mean, on the free group. So what kind of norm?
So what you say, so you take your free group, it's a tree naturally, so you can measure the distance in terms of the tree. So first you take the thing, this is a Fourier multiplier, okay? You take the Fourier multiplier with symbol some parameter r, which is less than 1 to the radius. So this is very good, but it's not finitely supported. I want it to be finitely supported, but then you truncate. And then what Riesz was able to prove using some delicate geometric argument is that this remains bounded. And this is something that led to a lot of interactions between geometric group theory and operator algebra. So that is very important.
It's not on the board. What is the question? To which the answer is yes.
Okay, so the question is, so given gamma, given a group gamma, does there exist a sequence Wn of functions from gamma to the complex numbers with finite support. Such that for every f in LP in the LP space that I just defined here, we can write f as the limit of okay, so this is a very ugly way of writing. Just we have the this is the Fourier. Maybe if it's better to write here lambda of gamma. So lambda of gamma is the operator of left translation by the element gamma on L2 of gamma, and so this is indeed the operator by convolution by Wn of gamma f hat of gamma, and I want to have this. And this has consequences only for the operator algebra. So I do not want to talk too much about operator algebra today, but this is as soon as gamma is not an abelian group, the question is in the world of operator algebras, and it has operator algebraic consequences. For example,
It's for every p as well.
so the question is given gamma and p. And yes, this is yes for every p, even 1 and infinity, all these groups. And actually, there is no counterexample. So it's open whether there is. So this is an open question whether this holds always, but I very strongly believe that it does not always hold.
So just to be clear, what's your set of groups that you like? Just any file? What's the condition on?
So far, any countable. Well, if I want sequence, maybe any countable group.
Needn't be finitely generated.
No, it's not very important. I think the question is as interesting. Well,
Okay.
you can take finitely generated groups if you want, but yes, the conjecture is that so some very simple group like the group of 3x3 matrices with integer coefficients should be a counterexample. At least, so I'm not completely sure for what to conjecture for general P's, but I have strong reasons to believe that at least when P is greater than 2 plus 2 over 2 minus 1, so if P greater than 4, it should be false, and this would be something that is very nice. And an evidence of that is a result that I proved some time ago with Vincent Lafort. We have a theorem that goes in this direction. And it says that if I allow operator coefficients, the conjecture is true. It says that for every p strictly greater than 4, there exists f in, so I will continue to use this strange notation. So I take values in operators. So what do I mean by that? So if maybe I can write here. So if I take a t, or if I have a function a from gamma to the bounded operator on h, I can define an operator on L2 of gamma tensor h, where this is the sum of the operator of translation by gamma tensor a of gamma, and I can define the p norm of that to be I take the absolute value to the p. I take the trace to do one. So just natural matrix amplification of the space. What we proved with Vincent is that when P is large, exactly as in the conjecture, there exists something that such that F is away from all its truncation.
Property of SO3Z you're using?
That's the whole topic of the talk today. So it's it's true for every hierarchical lattice over every any local field, real or non-Euclidean too. And I want to, my point exactly, I want to explain what is the harmonic analysis thing that we use. So the proof of that is a bit long. So it uses some geometry and combinatorics of the building or of the symmetric spaces, and it uses some basic harmonic analysis inequalities, but that are not Euclidean, that are spheric. So I want to insist on that. That's the whole. And I guess this is not very important because I will stop talking about arithmetic groups and I will talk about compactly groups. Okay, so of course, actually the main question is what about small p? And actually, I should have to explain why this is interesting. So if I take gamma to be SL, SL n of z for n large, then the condition becomes this one. So we have that. We have a condition that becomes weaker. Well, the interval where we don't know between 2 and this becomes smaller and smaller when the rank becomes large. And if we prove that this condition is not only necessary for the proof, but it's necessary for the statement, this would be very important for operator algebra because it would say that it would distinguish the fundamental algebras of these hierarchical lattices in terms of the rank, which is a well-known open problem. But so what I want to discuss now is, okay, what about small p and what comes into that, and what's the harmonic?
Now that you're talking about functional analysis, so the one thing is the reduced, if P is 2, it's reduced C, the reduced algebra.
So if P is infinity, it's the reduced algebra. If P equals infinity.
Okay, so why are you talking about von Neumann now?
Yeah, because actually as soon as you take the P completion,
yeah,
you don't see the difference between the fundamental algebra and the continuous. It's saying that in LP you have the infinity functions are bounded in LP, are dense in LP, but also the continuous functions are also bounded in LP. It's not true for P equals infinity, but as soon as you take P finite, you don't see any reason, any difference. Okay, and so the story of what I'm talking about today it started with this, where actually Javier Parcet noticed that the conditions that we have here are exactly the same that were here and the same as in the Bochner-Riesz conjectures. And this, so I first regarded the periodicity and that because the proof had nothing to do with the proof was purely representation theoretical, so it was not. I didn't know anything about harmonic analysis, but I had after some years of thinking about it, I have the feeling that there is more behind this numerical coincidence than just a coincidence, and that's the talk of today. Okay, so what is just to finish, the main tool is the following inequality: is that if we have, so if we work in the compact Lie group, so we take the group of rotations in dimension d plus 1. So if I have a function, a complex valued function on SO d plus 1, that is SO d by invariance. So this is just a very complicated way of saying that M of a matrix K is just some function of the 1, 1 entry of the matrix. Okay, so if we have a function on SOD plus 1 that only depends on the 1, 1 entry of this matrix, and if Tm, this is the Fourier multiplier with symbol M, if this is bounded on LP of in the split place that defined here, well, there is a small catch that this is not a discrete group, so we have to talk about integrals rather than sums, but this is a technical problem. Then we have that and P is greater than 2 plus 2 over D minus 1. Then we have that M dot is Hölder continuous. So this is a technical result, but that was really the heart of the proof. And this is the heart of the proof also of many other results about the geometry of higher rank lattices. So for those of you who have known about, heard about strong property T or the Zimmer conjecture about actions of higher rank lattices on manifolds, this is the analytic tool that is at the heart of all.
This is entirely in a compact subgroup.
Sorry?
This is entirely going on in the
Yes. So the analysis is there, and then it's just combinatorics of the symmetric space that allow to pass from this to this. So it's long, but it's purely combinatorial. Okay. And if we could say something interesting about this when P is between 2 and these critical parameters, this would transfer to also some meaningful statements here. So today I'm focused on seeing how optimal this is and how we can improve that. And in this direction, the very natural, the toy question that comes is, okay, let's take for a function M like this, that depends on the first 1, 1 entry that is as far as possible from being Hölder continuous. So let's take indicator function of some open interval. So the question is, let M dot of this is just the indicator function that S is positive, and then the question is the corresponding Fourier multiplier LP bounded for some P that is not. And this is this is a question that I've been thinking about for a long time, and it looked really like a very natural counterpart of Fefferman's multiplier theorem. And actually, well, and the answer is no. That's the new result of today. And we can do even better. We can actually essentially characterize in arbitrary Lie groups this kind of Fourier multiplier that are indicator functions of subsets. So the theorem is that we take let omega inside G. So this is a Lie group, and omega is a C1 domain, so it's an open subset whose boundary is C1. And we have that we can characterize the fact that Tm is LP bounded for some P. So this is the same as saying that Tm is LP bounded.
M is the indicator of omega?
Yes, M is the indicator function of omega. Okay. This happens if and only if this happens for every P. And this is equivalent to saying that there exists an action of your group like diffeomorphism on the real line. So maybe I assume to have a statement that is easier to state, I assume that it's simply connected to avoid some topological issues. So there exists an action of G by diffeomorphism on R such that omega coincides with the sets of elements that move 0 to its right, say. And this is locally. So of course we can have a for example in R2. So the indicator function of a band like this is just the intersection of two half spaces, and I'm just saying that locally it's a half space, but it can be globally a union of finitely many bands or this kind of stuff. Okay, so in particular, if since SOD plus 1 does not SOD plus 1 does not act by diffeomorphism. But you can yes. What I wanted to say now is that actually the theorem can be made more explicit, because Sophus Lee has explained to us exactly what are the groups that act locally by diffeomorphism on the real line. And so it says that we have 3 examples. We have R, say G1 is R, and the action is by translation. We have the affine transformations. Affine transformations of R, and then we have the projective transformations of R. So we take the universal covering group of SL2R, and the Möbius transformations, they act on the real line by projective maps. And we have 3 examples, so the theorem can say we get 3 kinds of Hilbert transform in this setting. So this is the usual Hilbert transform, and then we have an affine Hilbert transform and projective Hilbert transform, and thanks to Lee's results.
So that last one just acts on the extended real line.
No, what do you mean?
Or like the R union infinity.
No, it's not SL2 acting on. It's not SL2 acting on projective space. You have SL2 which acts on the projective space, but then the universal cover acts on the universal cover of a. So it's not what you had in mind. It's the other.
Okay.
So we have a third equivalence form, which is that there exists a quotient from G to one of the GIs, such that omega I is omega is just the pre-image of omega I. Well, omega I is exactly the example for the translation of affines or projective. And in particular, since SO3 does not have any quotient that is R, G2 or G3, we have that the original question has a negative answer. Okay, so this is the first half of the talk. This was only Fourier analysis, but for strange groups. I can understand that for some people this is too strange. So now I want to become much more concrete and work with matrices. So this is the second half of what I was. So far I've been discussing this question. Now I want to discuss this question, and the reason I want to do that is because actually the proof of that it goes by studying the question about matrices.
Sorry, what's the impact to the question of their?
It does not say anything definitive. It says that what would be interesting is if we could say that even when P is less than 2, the boundedness implies some continuity. And this we don't know. We have just said that boundedness implies that you cannot have a discontinuity in the form that you have a left limit and a right limit, and they are different. But for actually, even the question in harmonic analysis is wide open to my knowledge. So I discussed it with Charlie Fefferman, and he does not know any question of any result in this direction. So maybe I can write it here. If you get bored, you can think to that. So the question: take n, a function from R2 to the complex number that is radial, that only depends on the distance to the origin, and assume that Tm is LP bounded. So here P, not 2, is a fixed number that is close to 2, and the question is M continuous? Well, I think it's at 0 there can be problems, but that's not at all what I'm interested in. So is the symbol necessarily continuous outside of 0? And this is a funny question that people have not been interested in harmonic analysis. After Fefferman theorem, they were mostly, I believe, Bochner-Riesz became really the central thing. But this is a question that has some interest, I think, in analysis, and I'm pretty sure that if somebody comes with an answer to that, with the tools that I'm going to discuss now, we'll be able to answer the real question that was behind and that I don't know how to answer.
So your statement before includes the Ball multiplier.
Yes, exactly. So this is the statement that is below. It includes the Ball multiplier, and it says that actually if you take in RD, this says in RD, the only multipliers corresponding to open sets are smooth open sets are unions, intersections of unions of half planes. Here I put an assumption that the domain is C1, so that I do not allow in this formalism to have polygons, polytopes, but of course polytopes are bounded Fourier multipliers, but just because there are finite many intersections of half spaces. Okay. Okay, now I want to discuss what people call Schur multipliers. So it's a bit unfortunate that there are two Schur multipliers that have nothing to do one with another. So this is the one that corresponds to Schur product of matrices. So maybe since I'm French, I should say the Hadamard multipliers, because there's some people also call Hadamard product the product of entry-wise matrix. So if we have n of ij which are complex numbers, then this defines a Schur multiplier with symbol m. It's a map from the n times n matrices to itself, which sends a matrix A to a matrix A of ij, m of I. Okay, and again, what plays the role of the LP norm now is the sum of the LP norm of the singular values. So what is interesting is the P norm, which is the trace of absolute value to the power P to the 1 over P when P goes infinity norm, which is just the operator norm. And the question that we're interested in, okay, so take M, the indicator function of a subset of the set of pairs ij. When is it bounded for these matrices, and what are the norms? So of course, if I talk with finite dimension, it's always bounded, but the real question is how to make it quantitative and not depending on the dimension. Another way of making quantitative is that if we have x mu a measure space, and we have m a function of two variables, then we can define in the same way. If I take an operator on L2 of x, which let's say that it has a kernel, then I can formally look at the kernel M of xy, A of xy, and ask whether this kernel represents a bounded operator and whether this extends to continuously. And this is a way of making, if you don't want things quantitative, to make things in the infinite world. And there is a very basic example that I think, well, in the Western world, it's usually, well, maybe I will not dare to say who it's attributed to because I will misattribute it, but it's been long known for at least 50 years that a basic example of that is the triangular projections. If M of ij is the integer function that I is less than j, then we have that Sm is bounded. Well, let me say it's LP bounded for every p between 1 and infinity. And this is really in the world of matrices. This is the exact analog of the Hilbert transform, and it's even more than an exact analog. There is a direct way of relating the two. Is that so if we have a function in, let's say, a periodic function as before, what am I going to say? Then we can consider the matrix of Fourier coefficients that where I put at the entry ij, I put the Fourier coefficient with entry ij. And this is a matrix. And of course, if I apply the Fourier multiplier, this Fourier multiplier, this Schur multiplier to this matrix here, this is just where the HF hat of n is just indicator that n is negative. Okay, so just by this obvious formula, we can also and this is also, maybe it's better to do it like this. This is the matrix. This is the, if I consider the matrix f hat of I minus j that I multiply by z to the I minus j. So here I have a matrix that depends on a parameter z, which is z is a complex number of modulus 1, and that I here I multiply by the where D is a diagonal matrix with entry z to the r. Okay, so by this formula, we see that exactly there is a relation between the Hilbert transform and this indicator function. And we can ask in the same way, okay, now I want to state the same result as here, but for Fourier multiplier, for Schur multiplier. And the theorem that is the main tool to prove this one, it's something that says, okay, so if we take if X is it's a manifold, and omega it's a subset of X times X that is it's a C1 domain. And I also assume that it's transverse, meaning that the tangent space is never parallel to one of the factors. Then we have, we can also characterize, again, it's only local, we characterize the fact that the indicator function is LP bounded for some or all P between we can express it, so there are three equivalents. So the second one is that there is something that is non-curved in the same way as so that it's a bit, well, let me say, so for every point in the boundary and for every y in M such that we have the point x0m is also in the boundary, we have that the first coordinate of the normal vector to the tangent to the boundary at this point here is parallel to the first coordinate of the tangent vector at the other point. So this makes sense because these are two vectors in the tangent space at x0 in M. So this is what said that something is not curved. Actually, it can be made much more concrete. So it's a good thing that there are two submersions F and G from M to R, submersions, such that omega coincides with the pairs xy, such that f of x is greater than w.
What's M?
X.
Oh, the M is x, thank you. So forget for a moment about the second condition. This says that actually up to change of coordinates and amplification, the triangular projection is the only bounded multiplier, or they all come from that in a straightforward way. And well, once you have this very precise result about multipliers, you only show multipliers. This thing here becomes an algebraic question. Okay, so you have to do something like this to relate multipliers on matrices and multipliers on functions or operator algebras of this flavor. That is a bit technical, but once you have this dictionary, this is just a question of looking at what this non-curvature condition means in the presence of a Lie group and Lie algebra. And this exactly means that locally the boundary of this set is corresponds to a coset of a codimension 1 group, and that's exactly the kind of stuff that Lie has characterized. So I believe now it's 15 minutes is the end. So I
can take a few more minutes if you want, but also people don't mind being, you know.
Are you using Fefferman's method?
Yes. So that's exactly what we do. So actually Fefferman's bold multiplier theorem is two theorems. There was first Meyer's lemma, the lemma by Meyer that says that if if the bold multiplier was LP bounded, then we would have some square inequalities involving directional Hilbert transforms. So this was an observation by Yves Meyer, and Charlie Fefferman, using the Kakeya sets, proved that these kind of inequalities are not true. And actually what we do is we are able to in this setting to do some kind of Meyer lemma, so that we really the hard part is this implies this, and to do so we are exactly reducing to the Kakeya construction of Fefferman. We are proving some kind of square inequalities, commutative square inequalities for LP functions in the Euclidean space, and then using Fefferman. So it's the theorems contain Fefferman's theorem, but the proof also contains Fefferman's proof. Yeah. So, I could spend 5 minutes just explaining the idea of the proof, but I think what I said is enough, so I stop now.
Whatever you prefer.
I stop, yes, I
Okay,
stop.
so let's think of the talk first. So I guess we already had a bunch of questions during the talk, but are there more? So Peter already is.
The Kakaia sets that you're using are from RA.
Yes, exactly. So yeah. Initially, we had some more complicated way of kind of redoing Kakaia sets, but we found a much cleaner way to avoid anything new and only rely on the work of Fefferman, which is better.
So just to reiterate on this, so you don't need any kind of variant of Kakaia sets where you don't have straight lines, but something in like your manifold or something, right?
No,
that would be like the analog. I guess you could have like QD6 and cubes around QD6 or something, but none of this is like needed.
No, you don't need in this for this we don't need it. But actually, there are many other questions that for which we don't have the answer that for which I think we cannot reduce to Kakaia sets. So a very simple one is you take a free group F2 and you take the indicator function of the ball. Just you identify the free group with the four regular trees. So and you take the indicator function of the ball. And is this an LP bounded multiplier? So it has been known for 40 years maybe that it's not for p greater than 3. So the threshold is p greater than 3. So it seems if we try that situation is really as in the Euclidean case, it says that the free group should be 3-dimensional because it's exactly the bound that we obtain in dimension 3. But between 2 and 3, it's completely unclear, and it's rather clear to me that we need some new kind of Kakaia constructions that are not the one that we know in Euclidean spaces. And so yeah, here we don't do any new kind of Kakaia sets, but probably for other interesting questions we should.
In a semi-simple group case where you have these natural sets that come from radial, I mean, like you have this work of Nouveau and Stein, where you have almost everywhere convergence, maximal function inequalities for these growing sets that are special to, are they ever useful in this context?
Well, this theorem says
It sounded like how you're supposed to exhaust the space so as to get your finite dimension.
so. Before we had this theorem, this was the most natural thing to do was exactly to truncate along these spheres this theorem tells me that except in the rank 1 case, this can never work.
Okay, it's interesting.
Any non-Peter questions?
I'm just trying to make the speaker feel good.
Thank you very much. You don't really care.
In that case, I'll let you all get cookies. So.
Thank you.